I'm going to go ahead and introduce Dr. Rachel Smith. So she is the head of our Astronomy and Astrophysics Research Lab at the museum. And so she's going to give our special guest speaker an introduction. So welcome, Rachel.
Thank you, Carrie. Hi, everyone. I hope you can hear me okay, and I have my video on. So welcome. Exciting virtual week of astronomy days. And I hope if this is your first talk attending, that's great. If not, I hope you've had a great week. So I'm excited to introduce the first speaker of today. I think the first speaker of today, correct me if I'm wrong, Dr. Carter Emmart. And Carter and I are collaborators on a project that uses open source software called OpenSpace. Carter is the director of astrovisualization at the American Museum of Natural History, and their team is leading a NASA-funded project to fly through the universe, create this really great software and programming for fly through the universe visualization. And it is all based on real data. So you're gonna have a great talk today by Carter, who's probably the best driver of open space that in the universe, I'm gonna just say. So as an introduction, Carter, as I said, is the director of astrovisualization at the American Museum of Natural History in New York City, and he's been there since 1998. He directs the production of award-winning space shows for the Hayden Planetarium, and some of you may know that's the, so the director of Hayden Planetarium is Neil deGrasse Tyson, just to put some names together that you might already know. And these programs play worldwide. He's a co-investigator for the development of OpenSpace. That's the software you'll see today. His work in data visualization has been to draw together science across disciplines in order to show the broadest context of how we fit into the cosmic story. Dr. Emmart has been recognized as a pioneer in his field. He has an honorary Ph.D. from Sweden's Linköping University, which he received in 2006. And he also received the Technology and Innovation Award from the International Planetarium Society in 2016. Before the American Museum, Carter worked at NASA Ames Research Center out in California and the National Center for Atmospheric Research. And he's had previous careers as an architectural model builder and technical illustrator. He is, I'll just add, he's a wonderful artist. So well, I don't know, you may not be able to see any of his drawings, but he is an artist, and he'll be, he infuses all of his presentations with a great artistic sensibility. So Carter, without further ado, please take us to space. Well, the title of his talk is, is Seeing the Whole Universe, Are We Alone?
Well, thank you, Rachel. It's a pleasure to be with you all again at Astronomy Days. And thanks to Rachel, she keeps inviting me back, so I'm doing something right. I wanted to talk to you today just about the sort of special aspect of Earth and life, and especially at this time of the pandemic, where we're all too aware of biology and that we're part of a system, a global system. So what I'm going to do now is just share my screen here, and hopefully you'll all be able to see the beautiful Earth. This is an image that was taken 2 days ago. You see open space, and then with this, what I'll do is, so that I guess you can see me, is that I will do the following. So that brings me back into the picture. Does that look better for you all?
Perfect.
That looks perfect. Yes,
okay,
thank you.
Great. Okay. So just above my head, I guess, is Orion. It's hard to you know, to sort of understate how Orion is just very recognizable. So those stars and everything in this, as you'll see, is sort of a 3D atlas. Let's come a little closer to Earth. In open space, we're taking NASA data, and that this is published daily in a web browser, many layers that our Earth observing satellites actually produce. And they produce a daily global mosaic. And so this was taken, as I say, 2 days ago. And I'm now going to come up closer and closer on this image. And as I do, thanks to the internet, if it's being friendly with us, we will be seeing greater and greater detail as I zoom into kind of a special place. And so let me just do that. And let me make sure one thing is running. There we go. And as I come in, it was incredibly clear. Where are we right now? is off the coast of Northwest Africa. And so the Sahara Desert, and here we go. We're coming up on the International Space Station, and there it is. And so in this case, we see the ISS, and it's actually, let's just make sure, am I playing? Yes, okay. Now things are moving, and you can see that it barely seems to be moving, but we're moving at 17,500 miles an hour, but the altitude of the space station is 250 miles up. And from this perspective, and this is as far as astronauts have gone since we left the moon back, last mission to the moon was in December of 1972, which is incredibly long ago. We're getting on 50 years in the past, and we flew beyond low Earth orbit. So low Earth orbit is just 250 miles in altitude. To compare that to sort of, I like to think of Pennsylvania. Pennsylvania is about 300 miles wide. So the altitude of the space station is not really that high, but I bring this perspective to you right now to sort of talk about Earth and what we see. Here, as we approach the Sahara Desert, we can see really just the ground. Because it's desert, there's very little vegetation there. Because of the circulation of the Earth's atmosphere, it creates a sort of devoid zone of vegetation, but it allows us to see the bare Earth, but also the beautiful blue edge of the Earth. And that atmosphere, we've done a lot of work with open space. We have a physics-based atmosphere, and that means that we produce a rendering of the Earth accurately portraying the atmosphere, which is very important to show. It's only 20 miles thick. Now, when I'm not up here taking care of my mom during the pandemic on Cape Cod, that I live in Manhattan. So I live on an island which is about 17 miles long. If you stood Manhattan up at Bowling Green at the bottom, the tip of Manhattan, that the top of the island would barely be sticking out of the atmosphere. The atmosphere is incredibly thin compared to the entire globe. Now, also, what's nice is if I pan upwards a little bit, it's hard to see the geography. We see the clouds, and we're flying over the Canary Islands. These are volcanoes that are down below us. And then, but the prevalence of the ocean is really the main point here. We are a water-covered world. Now, I mean liquid water. And also, we can see another aspect of water. Just when it goes into the vapor state, of course, it creates clouds and creates weather. And up at the poles or at the tops of the mountains, of course, we see snow. So we're a world where water sort of defines the globe. Let's pull away from the space station now, and we'll gain this broader perspective. And that we'll see this globe of ours is really extraordinary in the sense that it's, we call it the blue marble. It's 70%, so 3/4 covered by liquid water or our oceans. Of course, life as we know it depends on water. We as animals, we depend on drinking fresh water, which is a small component of the total of water on the surface. But water really characterizes the view of Earth. Now also, the atmosphere, even though it's super thin, as I just showed you, it also colorizes, it scatters the sunlight and gives this sort of veil, almost jewel-like, of the atmosphere. And if we look at the atmosphere that we have, we're dominated by nitrogen, but we also have oxygen. And oxygen is something that if you left just, sort of geology without any life there, you couldn't really support an oxygenated atmosphere. You need life to be creating the oxygen that we see. And if I pull around this way, what I'm swinging into view, it may not be immediately recognizable, but this is South America. And once I'll just pull a little bit closer to it. Let me center on the Earth. I was centered on the International Space Station, so I'll just center on Earth now. And what we're seeing is South America. And the reason it's veiled is that especially in the northern part, which I'm centering now, coming in underneath the clouds is the giant Amazon river basin. And of course, this is the Amazon rainforest. And that thick cover of vegetation is basically breathing. It's doing this transpiration of water. And so it's creating the clouds. And the clouds come and go with every day when underneath the lamplight of the sun and it warms up during the day, tends to rain out at night. So it's this balance of these systems of life that makes Earth just amazingly beautiful and also the most colorful planet. Because we have the browns of the ground, as we saw in the desert, but we have the green of the veil of life, of vegetation, which all other life sort of feeds off of in our food chain. Not to mention where life started, really in the oceans, and so that tremendous amounts of life in the ocean itself. And then I was showing a little bit of Antarctica. Here we can see at this time of year, it's winter in the northern hemisphere, so it's southern hemisphere is summer, and so the Antarctic ice cap is exposed to the sunlight. I thought I'd just bring around to this side. This is a nighttime image, which is also gathered by satellite. And it's highly illuminated because last night was a full moon. And this is a couple days ago. But where we were looking at the day in America, the Americas, North and South, and a little bit of Africa, here, what part of the world are we looking at? I'm looking at East Asia. So right now I'm coming in over China. So I see the clouds, but also this is kind of a black and white image. And I'll sit here for a second. We see the nice swirl of the cloud, but we also see lights, and these are city lights. So this is the illumination of humanity and our cities. And over here in China, we have over 1 billion people. And we have also down here in India, another 1 billion people. And they're supported by the Himalayan mountains, which are sort of, I'm zooming in now on, and the Himalayas are the tallest mountains in the world. And so they have a lot of snow that builds up. And when that melts, the glaciers melt, basically it sources rivers. Like the Ganges in India and like the Yangtze in China. And the populations depend on that water coming down from this, again, this system of Earth, this system of water, which is this tremendous planet that we know and love. It's home, and it's out here in space. Of course, we're the third planet from the sun. I think what I'd like to do now is I'm going to turn on some lines. These lines illustrate trails. They show where the Earth was. So this blue line shows sort of a history of where it had been. And if I pull around to this side of the Earth, we can see it goes off into the background. There's some other lines. So this is an orbit trail. So this shows, where we are, but where we've been. And if I pull out far enough, we can see that there's something prominent that goes around us. Goes around the Earth. And of course, that's our moon. And the moon is incredibly far away from us. Remember, we started off with the International Space Station. And so what I'm going to do is bring up a line for that as well. So that we just recap where we started and that we see the moon in the background. I just want to come a little bit closer now just to remind us, okay, the International Space Station, we visited it, but we didn't really get to see how high it was in seeing the whole Earth. Remember I said that it was about 250 miles in altitude above the ocean, and that's not really that far away. The moon, by comparison, we see it there in the background, barely, and it's 250,000 miles away, so it's 1,000 times the altitude of the space station. And so what I'm going to do now is turn on some other satellites. And I'm going to speed time up just to make this a little more fun for us. Let me go to minutes here, and I'm operating open space on a separate window with its user interface. And now we see the satellites going around. And if you come in close, you can see up close to the Earth, look how fast they go. Remember, I said we were traveling at 17,500 miles an hour at space station, but it didn't seem to be moving very fast. I'm now moving a time lapse here of 16 minutes per second. And so, in fact, you see kind of a gap in the Earth coming around. That's the international date line. That's this mapping of Earth that NASA does. And at this point, there, it changes to a map. This is why I didn't use yesterday. It was an incomplete map because the satellite had a problem. So let's just keep going with this. I want to move out. So, the farther away we go from Earth, the slower the satellites are. And you can see this prominent belt out here, which is parked above the Earth's equator, in fact. And these are our geosynchronous satellites. The space station goes around the Earth in an hour and a half, so in 90 minutes. But these satellites out here at about 23,000 miles, they go around the Earth every 24 hours. So they match the rotation rate of Earth. And so from the ground, you see that satellite, oh, it's just always up there in the sky, parked at a certain place, which is perfect for sort of radio communications.
So Carter, we have a question from the chat. So Anne wants to know, are the satellites that are not around the equator, are those in polar orbits?
Yes, in fact, the satellites that are in between the ones up close to the Earth, like the space station, those are the low Earth orbiting satellites. Then we have the geosynchronous satellites that I just explained. And then the ones in the middle tend to be global positioning satellite, GPS satellites. And so they sort of occupy this realm in between. But thanks for that question. And I'm glad you asked it because there's a lot to see that I'm showing in here. The distance of about 23,000 miles out to the geosynchronous satellites is 1/10 the distance to the moon. So now let's focus on the moon. And I'm going to take us there. Now let's see, I'll just zoom out to it. And as I get out to it, remember I said we had this set for 2 days ago and then time was progressing. So it's sort of approaching now. That it's, and if your weather was nice and clear, it wasn't where I'm living right now in Cape Cod. We had a storm last night, but you would have seen a full moon. So here we see the moon almost full. And now it's gray, no color. That's the first thing to notice. Also, I should point out, the moon is 1/4 the diameter, 1/4 the diameter of Earth, smaller, so less gravity. That's part of the fun part of going to the moon. You're 1/6, you'd weigh 1/6 your gravity. So, you know, if you weigh 100 pounds on the Earth, you'd weigh 20 pounds on the moon, and you can probably jump 6 times higher. And so those things are fun about the moon, but there's no air. You need to wear a spacesuit. But when people first looked at the moon, they looked and they saw these gray areas and lighter areas, and you can see that with your eyes. But with early telescopes, they saw a moon picture that kind of looks like this. Let's get a little closer. As we started to look with better telescopes, we could see that the gray areas are smooth. And so I'll just tip over so that we can see that. We see all these holes. Why are they holes? Well, on Earth, we know where things are round at the top of mountains. We know those are volcanoes. And so the volcano sort of lets out gas and lava and stuff like that, and then relaxes and goes quiet for a while. Sometimes they come back, and it usually leaves a crater at the top of the mountain. So people thought, well, maybe these are volcanoes. But as an argument grew up later with scientists, because they know that round holes could be created by impact craters or asteroids or plowing in. We now know that all these craters we see right now are impact craters from asteroids. And so the moon has been hit by asteroids. The Earth has been too. But because we have this active cycle with water and ice and rivers and erosion on Earth, that's constant, that has erased the craters. We do see in certain cases certain craters on Earth, but they tend to be young. We went to the moon And when we went there, we actually sampled the lavas, the smooth areas. First of all, we wanted to land in a safe area. So we landed over here in the Sea of Tranquility. It's just coming sort of into darkness. It's just below us here. So we landed there because it was safe. But then later, in later missions, we got closer to craters, and we brought the rocks back, and we could date them in the laboratory. And we now know that the moon rocks that are from the smooth areas are about 3 to 3.5 billion years old. And where we got areas like at the edge of this very large impact basin, we call it the Sea of Rains. Do you see how big, smooth, circular area? It makes up one of the eyes, the old man's eyes of you look at the face of the moon, the two big eyes. This is the bigger eye. And the edge of the moon, where the mountains are, we found the oldest moon rocks of 4.5 billion years old. So we're talking about things that are very, very old. The oldest Earth rocks we know of are on the order of just shy of about 4 billion years. We understand that the Earth and the moon sort of formed together, but they couldn't be more different. And these smooth areas seem to be where lavas did upwell, so that in this early time, from like 3.5 billion years ago, very large impacts, the moon was still warm enough in its interior that lava flowed out, filled in these very large sort of impact basins or craters. I can come to another one over here, which we don't see because it's sort of on the edge of the moon as seen from Earth. The moon always shows one face to us because it's called tidally locked. That one face is what we always see. But over here is the Eastern Sea, Mare Imbrium. And what's beautiful about this is it shows lots of mountains, but it kind of looks like a very big crater. And in the middle, you see dark areas, which were the lavas, the lavas that filled in. Okay, we went to the moon. There's no air. It's very old. There are lots of craters because of asteroids falling in, and that's erased on Earth. But we did not expect to see any life on the moon, and we haven't. We need water on Earth to really have life as we know it. And so we went to the moon. It was very interesting, but it was early in the space program, and really just on the edge of when we had started to also send robots, space probes, off to beyond the moon to the planets. I'd like to take us now to the sort of most Earth-like planet in the solar system, Mars.
So Carter, before we leave the moon, I have a question. So Allison says that side is a lot of craters. So why are there more craters on that side than on the other side?
Well, this gets into this story I mentioned with the tidal locking. And what that means is, you know how tides on Earth we have, because the moon actually pulls on the ocean, and it has this gravitational effect, even though it's orbiting us from so far away, 240,000 miles, 250,000 miles away. And so that force that it exerts pulls on our oceans, creates these tides. And in exchange, Earth is, of course, also pulling on the moon, even though it's orbiting us. So the near side of the moon, in fact, what I can do here is actually, let me just turn off the sun lighting on Earth. So let me see, Earth, focus on moon, hello. Oh boy, okay, just give me a moment. I knew this question was going to send me down a rabbit hole, but that's okay. That's what's nice about open space, is that we can really sort of look at these things and talk about them. So here, if I turn the sun lighting off, we can see this is the side of the moon that faces us, always faces us. In fact, I'm going to stop. I have time moving quick. I'm going to stop the time. And so this is the side of the moon we know and love. It's sort of the face of the moon, two eyes. If you turn it sideways, we kind of see a rabbit shape. Can you see the rabbit, sort of the base of the rabbit's body on the bottom, then his head and the ears. And in Asia, they talk about the rabbit in the moon. I like that. So the moon has all these volcanic, smooth places where lava has upwelled from giant impacts. making this smooth side of the moon. The far side of the moon is almost entirely craters. We can see the Earth in the background. There's also, Rachel loves this, there's a seam on the moon. This is data. This is data from a satellite. And the providers of this map, the U.S. Geological Survey, have provided a map that has a line down the middle. So think of it as the zipper on the far side of the moon. There is no zipper, but this is just an artifact of the mapping. Why is this? We believe, and we actually, well, we know this now from measurement, is that the crust of the moon is thicker on the far side. It's also lighter. And on the near side, where the lava came up, the crust is thinner. That means that the center of the moon, where it's heavier, is displaced on the side toward the Earth. Like a pendulum over time, that this side of the moon has swung toward always facing the Earth. And as it goes around the Earth, it rotates, but it rotates in such a way that this side is always facing the Earth. So we call this the near side, and this the far side. And if you've heard of the dark side of the moon, well, that just has to do with any planet. On Earth, we have a dark side of Earth. We call it night. We have the light side of Earth we call day, and the same thing happens on Earth. So, but that's a very good question. And you can just see how many craters there are. We call this crater saturation. It's just crater upon crater upon crater. All right, so we move out now, and I want to just emphasize distance again. There's the Earth, there are the satellites. This is 250,000 miles away. This is the farthest humanity has ever been into space, and we did that 50 years ago. Hard to believe. But I want to now, let's see, I just want to get this in a way so that there's Mars, it's that red line. We have, I'll show you the logic of this. Let's move away slowly though. There we see the moon around the Earth, the satellites, and as the moon almost disappears just into the trail of our orbit around the sun, we now see the orbits of the other planets. I can turn on a label. There's Earth, there's Mercury, there's Mars. Well, hey, where's Venus? Venus is in between, there it is. And we see beyond Mars or Jupiter, Saturn, and you see the planet Pluto. I still think of it as a planet. I'll give my plug right there. It's a small world. It's smaller than our moon, but very interesting. So anyway, let me now focus on Mars. And let me do that with my menu. So we just move a little bit over here. I'm going to turn the labels off. Now, just as the satellites that were closer to Earth go around faster than the satellites farther out. In fact, the moon goes around. Does anybody tell me how long it takes the moon to go around the Earth? Any answers out there?
Let's see. How long does it take for the moon to go around the Earth?
The answer
Annette says 28 days.
That's very good. That's one moon.
1 month. One moon.
Exactly. So moon is approximately, that is correct. And so what I'm pointing out here is that Mercury goes around the sun in only 88 days. The Earth goes around in 365 days. It takes almost 2 years for Mars to go around the sun. And so that a Mars year is effectively almost 2 Earth years. And that I'd love to talk about all the planets, but I'm going to focus on Mars here. Just going to look at my time as well. Great. And so I'm now coming up on Mars, and let me just make sure that, give me a second. Great. And what I wanted to do is turn on, there are different maps I'm going to show you of Mars. Yeah, I'll get to that in a second. Now, of course, we have our moon. Mars has 2 moons, Deimos and Phobos. They are small, about asteroid size, a few tens of kilometers in size. And so much smaller than our moon. I could talk a lot about them, but I want to really focus on Mars. And so here we see Mars. And if we just look at it first, as astronomers did, we see that, well, even before astronomers had telescopes and we were just using the human eye, we could see that Mars was reddish in color. It's reddish brown. We now know that it's covered by iron oxide. And so why is that? And you know, we thought when we looked at Mars, we saw it had seasonality. We could see that it had poles of ice. In fact, we might be able to just barely see the North Pole in this view right here. And there's a little bit more, you barely see it maybe. But anyway, so Mars has poles of ice like Earth. We saw that it does have ephemeral clouds sometimes, and but it was predominantly this sort of reddish color. And because it was the next planet out, we thought, well, it receives less sunlight, so it's going to be colder. Its red color does not mean it's warmer. Some people get that confused. Venus is very warm. That's closer to the sun. It also has a greenhouse effect, which is another topic that has having to do with atmospheres. But Mars, first of all, let's talk about size. We know that Mars is between the size of the moon and the size of the Earth. It's half the size of Earth, twice the size of the moon. So it has enough gravity to hold on to an atmosphere. And then we see these dark features and light features. Well, what was that about? Well, in fact, I'm going to come over here and just emphasize that when we got to Mars with an orbiting spacecraft for the first few times, we flew past Mars with probes. In the same way we flew past a few years ago, Pluto, we just flew past it and took pictures. Mariner 4 in 1965 flew past Mars and took a string of pictures across the surface. Where it looked, in fact, it looked over here. This area right through here doesn't look like much. It saw craters. Well, if I come close now, we can start to see things that look like craters, like the moon. And we were kind of disappointed. We might, because some people conjectured maybe there's a civilization of Martians there. Well, what we saw was a lot of interesting geology, craters, but it looked more like the moon than the Earth, and we were disappointed. When we got to the moon with an orbiting spacecraft in 1971, it was called Mariner 9. We got there and there was one of these global dust storms. Tends to happen about once every Martian year. We have dust storms. In this case, it was a big one. And all we could see were what you see in front of you now. We saw 3 dots and 1 dot off to the side. And we were very disappointed. I was like, oh, we got here with our orbiter and now we have to wait for the dust to clear. And we had to wait months. But what we came in on and what we saw through these dots, I'm going to come up to the biggest one, was the largest volcano in the solar system. This is Olympus Mons. This is taller than Mount Everest by a factor of almost 3. And we have a central area here, which is this crater or caldera up at the top. Let's make this easier to see. So what I'm going to do now is turn on a higher resolution map. And then also I'm just going to adjust the time. And also this map has been a little bit slow. It's loading over the internet. Give me a moment here, and I'm just going to try to goose its, let's see, I'm just waiting for this to come in. This is, oh boy, oh, there it goes. Okay, a little frustrating. So here we see the totality of this volcano. Now, this is satellite data. That's why you see some little areas that have not actually been imaged or photographed by the satellite. But with Olympus Mons, we see there's a cliff around the edge of it. We don't exactly know why. That's still kind of an open question. But if I come a little closer, we can see the caldera. Hopefully that will come in a little faster. But if I come over here, this is on the western side, we see kind of streaks coming down the flanks of the volcano. And this illustrates where lava flows have come down. And this caldera in here, oh, nice, it's coming in. is about 50 miles across. And when I give presentations in New York, I like to say you could take New York City, which is made up, of course, of Manhattan, the Bronx, and Brooklyn, Queens, and Staten Island, that you could fit all of that easily inside this caldera. So it's huge, largest volcano in the solar system. And if I come in close enough, we can then sort of tip it over, and we can see that the height of this, once again, about 3 times the height of Mount Everest, is so high that it sticks out of the atmosphere of Mars, and we can see the stars above it. Now, this is a volcano. Gases come out of a volcano. And so on Earth, we have active volcanoes. Of course, we all know that and watch the news, and there's usually a volcano going off somewhere in the world. And but on Mars, we have these giant volcanoes. They don't seem to be active, and they don't seem to have been active for quite some time. These are 3 other large volcanoes. And then, of course, there's the famous canyon. So what I'm going to do now is just, I want to advance time here in such a way that, actually, I'm going to go just adjust this so we can now see the canyon on Mars. Where these volcanoes appear, Mars appears to have bulged up and created a crack from the bulge. If you've ever cooked bread or cookies, you know how when it rises in the oven because it has yeast in it, that it tends to dry out and crack on top. Well, Mars seems to have done this. It bulged up and created this giant crack. If any of you have ever been to the Grand Canyon on Earth in Arizona, the Grand Canyon is about the size of the canyon we see over on the right here. This is a tributary canyon into the Valles Marineris, and this is named after the Mariner 9 spacecraft that discovered it. So the Mariner Valley, or Valles Marineris in Latin, and so that we can now see this tremendous canyon. I draw your attention to, okay, there's this active geology. There are sulfurous layers, sulfate layers that are at the bottom of the canyons. Sulfur comes out of volcanoes. Well, I'm telling you about this the volcanoes. We see a thin atmosphere on Mars today, and it's so thin that you cannot really have liquid water on Mars. But we see ample evidence of where water must have been in the past. So let me just come over here. And so no water on the moon. Remember that? It's just not even enough to have an atmosphere and so forth. But if I come up in this area, there are areas that look like these are the outflow channels on Mars. There was clearly something fluid that was released catastrophically and flowed out, leaving areas of knobby terrain that we see down here. It's called chaotic terrain. And then these giant river channels, these channels that were carved, moving tremendous amounts of material out to lower elevations. And so the water is flowing, in this case, toward the top of the screen, which is north, into a lower lying basin called the Chryse Basin. And so we see that there was water on Mars. How old is this terrain? Well, we don't have a sample of Mars. We have some meteorites that we know are Martian, so we can date those. But in order to date these areas, we really have to go there and bring samples back. But we can compare the cratering we see here to the moon, and we get a rough idea that this area and where these channels flowed is about 3 billion years ago, about the same age as the Mare basalts on the moon. Mare being the smooth areas I talked about. Mare is the Latin or Italian word for sea or ocean, because we thought the smooth areas on the moon might have been water when we first looked, because it was smooth. This indicates that Mars, at least in the ancient past, possibly had water. Well, where did that water go? Why is Mars dry and Earth was wet? And why was Mars wet at one time? Mars, being half the size of Earth, cooled off faster because it has less insulation. Earth still has some of the energy of its formation, as well as we believe it's the radioactive decay of radioactive elements that heats the Earth. We also know that Earth has an active sort of gooey, liquidy interior, not only because of seismology, and we can kind of trace from an earthquake the interior stratification of Earth, but we can also tell it's active because we have a magnetic field which diverts the effects of the solar wind. That's another topic. But Mars, we see areas of magnetic niches or archaic areas on Mars that have slight magnetic fields, traces of a magnetic field, but no magnetic field today, which is another indication that Mars dried up and of massive climate change. And so Mars is an interesting story where water possibly was. I'm not going to take you to Jezero Crater, which is where Perseverance is going to land next month. That's another topic to get into, but we're going to look in a place where we know that there was water. It was a lake. Where there is water, possibly life. So now let's leave Mars. Let's look at the solar system and let's consider where life is and where life isn't. Well, Mercury is smallish like the moon. It's bigger than the moon, but no real atmosphere to speak of. Venus has a tremendous atmosphere, but a runaway greenhouse effect. You can melt lead on the surface of Venus. It's a terrible place, but it does have an atmosphere. Venus also seems to have been different in the past. So we have to consider the evolution of the planets, but that blue line is us. Too close to the sun, too hot. Too far away, Mars, cold, but liquid water, perhaps in the past, a thicker atmosphere supported by volcanoes, but not anymore. The atmosphere is thin. So there's kind of a Goldilocks zone, if you could think of the solar system, that we are the winners insofar as the liquid water story, and we're here talking about life. Life is complex chemistry, complex chains of molecules with energy to drive the making of complex chains and the regeneration of information, which is life. That's us. We go farther out, we're getting farther and farther away from the sun, colder and colder. But let me just quickly show you another world where we know that there is water. And out here at Jupiter, we did not expect this at all, but Europa is a very interesting world. I'm coming up to it. It's the second of the 4 large satellites discovered by Galileo with a simple telescope. In fact, in binoculars, you can see these little star-like apparitions that seem to go back and forth next to Jupiter. And so we're now looking at a world not too different in size than our own moon. But if we look at it, we can see and we know it's icy. And we know that it's ices. And we see one crater here. But look, the fractures on this. It looks as though this is, a broken up ice flow. And we believe that that's what the case is. We now know, we have evidence that there is a liquid water ocean underneath this icy surface, with more water than on the planet Earth at its surface. There is water there. And to keep it liquid, there has to be an energy source. Well, I'm just going to quickly show you the idea for that energy source. And I'm going to go to it. It's the next moon in, Io. Io is covered by volcanoes. In fact, it's the most volcanic world in the solar system. And it's got these colors of this sulfurous covering. So it kind of has this sort of pizza color. Io is very active because Jupiter's gravity pulls on it. And then its own gravity wants to keep it a sphere, but Jupiter wants to sort of pull it into a potato shape. But then the passage of Europa, next moon out, means that there's this sort of gravitational back and forth. And that is enough to flex Io, and it flexes it enough to create an energy source to melt the interior that comes out as volcanism and drives volcanoes of Io.
So is
So
that
the,
Allison is asking, are those black spots the volcanoes?
yes, 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 they were. And if I just come back to Europa for a second, I'll just draw our attention once again to these sort of ice flows around it. And that we, in flying past Europa, there's a tremendous magnetic field generated by Jupiter. And there was an effect on the that magnetic field caused by Europa called magnetic field inversion, and that must have happened from a salty ocean underneath. And that's the evidence for this. We're sending a mission there, Europa Clipper. I want to just turn our attention quickly to Ganymede, which is the largest satellite in the largest moon in the solar system. It's larger than Mercury. And I just got to quickly look at it. And we know it has aurora. It has a magnetic field. And if we look at this, we can see patchiness, which belies, we know that it has ice. It's just based on like the mass and the size, the density, that it's a world of rock and ice. But we can see things that also kind of look a bit like Europa. We know that there is water underneath this frozen crust here as well, and liquid water. Where there is liquid water, there could be life. Now, we need sort of life to make complex chemistry and all that. We need an energy source. We have that on Earth with sunlight, but here we have this sort of mechanical energy source that creates the volcanoes on Io, and then these icy worlds around Jupiter with water. I'm going to go to one other world here, and hopefully I'm just looking at my time, which I don't have much more time, but I'm going to go to Titan.
Yeah, we have about 4 minutes.
Okay. And if I just go to Titan, Titan is a world, there's Titan and Enceladus. Enceladus actually has geysers, but I can't really show those to you. But in the case of Titan, which is also larger than Mercury, it has an atmosphere of methane. Water out here on the surface is so, this is a radar image that we see, and then we see the atmosphere. Water is so cold here, it's about the hardness of granite. But we see evidence, especially up at the poles with Titan, at Titan, we see lakes, and these are hydrocarbon lakes. These are lakes of ethane and methane, and but these are sort of the building blocks, is carbon and hydrogen chains, which are the basis of life back on Earth. We also know that Titan has liquid water underneath its surface. So if we just look at the entire solar system now in this last couple minutes, is that we see our place out here in the universe is that around the sun are places for liquid water and for life. Is there anything else out there? Well, let's actually show very briefly here. I want to close all this out. And
so Allison has a question. Has anyone ever explored the water under some of Jupiter's moons like Europa?
We're about to do that with radar, with the mission that's going there explicitly to look at that, and that is called the Europa Clipper mission. And so that's very much in the planning. In fact, a very close friend of mine is heading up that mission, Bob Papalardo at the Jet Propulsion Laboratory, and he's been planning that mission for his entire career. He's an expert in icy satellites, and so it's great. What I've just brought up are exoplanets. You've heard about these. These are locations that I show you here of stars. So this is a map of where those stars, of where they are. And in fact, over here, Kepler results, we looked at just a patch of sky. You see a footprint of the detector. It looks like a waffle. But all those little points are stars that have planets. We thought, well, when we got to the moon, maybe life is only on Earth. And then we saw evidence of water around Mars. And we saw evidence of water, liquid water, in the outer solar system. We now know of many, many, many more planets. I've left the solar system. We're out in the stars, and we're now looking at a three-dimensional representation of planets just that we've found since 1995. That was the first one that we found. And now we know of sort of planets in all directions around us, the blue ones that we see here. And then if we look at the Kepler results, that's just one part of sky we looked at. So we know that finding planets is the norm. And let's see, I froze for a second. Let's pull out and see the greater part of the galaxy. Now we can see the Kepler results against the Milky Way galaxy. The galaxy is huge. It takes light 8 minutes to go from the sun to the Earth at 186,000 miles a second. It would take 100,000 years for light to travel across our galaxy. I show you those Kepler results. We can see them. They illustrate just what we see close to us. We now know that the galaxy has about 200 to 300 billion stars. If you do the math and say, oh, they have a few planets each, maybe 10 planets each, we easily have 1 trillion planets in a galaxy. Look at all the other galaxies in this atlas now. The Milky Way, will come back there in a second. And we now see in the digital universe, which we visualize in open space, we are now seeing accurately displayed here the galaxies that surround us. And these galaxies go far away. These, every one of these points is another galaxy. Every point is several 100 billion stars. Every point is perhaps 1 trillion planets. This is a mapping of galaxies that reach out to several 100 million light years. And now we see a map that goes farther out. It's hourglass shaped because where it's black between is where we see our galaxy, and it kind of blocks our view to either side. That's why it's hourglass shaped. And as we go farther and farther out, we see more and more galaxies. And so this is a charting of the universe. And now, if it's rotating in front of you, it's almost shimmering as just the way the visualization shows the points of literally about 3 million galaxies we've charted so far. There are many more than this. If you're young and you're watching this and you're interested in astronomy, you will probably be filling this picture in your career. But what's amazing is since 2000, the year 2000, since I've been working at the planetarium, that we have put this map together. We meaning humanity. This is the Sloan Digital Sky Survey from a certain astronomer's team. And then the exoplanets, we saw the Kepler mission and results of other astronomers. This is the sort of the giant jam session of science that we put together into what we call open space. And so I'm going to come back home now, and I'm sure I've blown past my time, but I just want to ask you here, you know, if life is only on one planet, it's an awful waste of space. And so, you know, that life being out there, well, we don't know. We only know of life in one place. But when you look at the universe and you see the stars, when you look at the universe even farther and you see the galaxies, are they not eyes of life looking back at us? That's really the big question. Thank you. And it's been a pleasure to present to you today.
Oh, thank you so much, Carter. This was just fabulous. And so we are having a debate in the chat, and I think most of us agree that we don't think we're alone. So,
well, good. I agree with that.
So let me. So I'm gonna, if you don't mind, I'm going to share my screen, and y'all tell me if you see it. Can y'all see my T-shirt screen? So Carter, thank you. Rachel, thank you so much for participating in this program. I want to thank North Carolina Space Grant for sponsoring Astronomy Days this year. And I want to thank all of you for attending today. We do have some merch at the museum store, some awesome Astronomy Days t-shirts and hoodies. So please go check that out. members get a discount. And if you are not already a member, I hope you consider joining today. We have our next program is Astronomy and Film. And pop that link in the chat for you. It's going to be really fun. So we've talked all about, is there life out there? Well, films say yes. So we can check out how accurate some astronomy students think that is. So thank you so much, everyone. Have a great rest of your astronomy days.
Thank you, Carter.
Thank you, Rachel. That was fun.
See you next year in person.
Okay, cool. All
Yes,
right.
please.
Thanks, everybody.
Fingers
Download
crossed.
Open Space. Bye-bye.
Bye.
Bye-bye.